Okay, welcome to Wednesday. So the other day we finished off with some AVL stuff. We're going to continue doing that today, and then we're going to go into one of my favorite data structures, a thing called a trie, which we will get to in a little bit of time. For those of you who've been paying attention to the schedule for the class, I apologize. Up until today, it's been like completely screwed up, and I tried to I went and looked at it today and went, what did I do? So things are, I think, back in order now as far as where lectures happen and all that. Next Wednesday is the midterm exam, and it's going to be in here, regular time, and 1 hour. You do get a back and front piece of paper with that you handwrite. None of this business where you're like typing it up and bringing a magnifying glass and seeing all that. Although I would probably like give you props for that. I'd take it away from you. But that's the way you can do it. One time I heard of a person who the professor said, hey, you can bring anything into class that you can carry into class, like whatever. And somebody ended up like carrying a graduate student in with them, and sitting next to each other, and then hey, probably did well on the test, and I'd give him props for that too. So anyway, so that's the exam. On Monday we will have a review session for, the class will be review on everything we've covered so far, including today's stuff. So everything up until today will be possible to be on the exam. OK, questions on that? OK, let's go back and remind ourselves about AVL trees. OK, AVL trees are binary search trees. And what is the AVL invariant condition? What is that all about? Somebody from this area. Somebody with a sandwich in her hand. No, I'm kidding. I'm kidding. What do you guys think? What's the AVL quality? Yes? The height for any node, the height of its subtrees can only differ by one amount, right? So if you have a binary search tree and then you go to a particular node and the heights are different by more than one, it's not AVL and you have to fix it. OK? And we fix it using these things called rotations. And if you remember, we did a whole bunch of single rotations the other day. If you insert something on the right subtree of the right child, and a node becomes out of AVL because this is 1 and this is 1, 2, 3, then you have to rotate which one of these? Careful, we say that we rotate K1 is the one we say we rotate. In which direction does it go? It goes to the left, to the left. And we do that by grabbing on and holding on to which one? K2. You lift up K2, and everything shakes out under it. You don't change this link. That's the one I think I kind of didn't glossed over that. You don't change the K2, K1. Whatever happens to this one has to fall. In this case, it has to be because y is bigger than K2, less than K2, but bigger than K1. It's going to fall on which side of K1? To the right. And if you'll notice over here, this is what happens. We grabbed K2, we pulled it up. K1 just kind of falls down there. And then the y goes from the K2 over here, and it goes to the right of K1. OK? And it works out if you work out the math of the arithmetic on what's bigger and smaller. OK? The exact symmetrical case is for if you inserted in a left subtree of the left child, and a node ended up out of AVL. OK? So that's reminiscent of this one. Yeah, Nathan?
So just to be clear, there is some pointer manipulation.
There is going to be pointer manipulation, yeah. And in fact, for this homework assignment, first of all, some people have come to me already about this homework assignment and said, remove. I don't get remove. It's not working. Remove is very tricky, correct? Remove is pretty tricky. And it's tricky in the sense that, remember, there are lots of cases for remove. And you have to be very particular about when you actually change those pointers. So be very careful about that. I'm considering, let's see, when did I say this was due? Next Friday? Oh, I'm not going to be here next Friday. I was thinking next, sometime midweek, having a little review session on that. But you've also got the test in there, too. So we'll figure something out. But it's definitely a tricky thing to do that remove. So start it early. Again, as I said before. But to your point, yes, we do have to do node changes. One other comment on this homework assignment, it is not AVL trees. Okay? The homework assignment is strictly binary search trees. It is not AVL trees. Now, if you want to go above and beyond and do an AVL tree, great. What you probably should do is do the binary search tree, get it all working, copy that file, and then make the AVL tree. So you don't try to because it will break. If you try to do it AVL, it would break all our tests on the regular binary search tree. So if you wanted to do that, that would be a great above and beyond sort of thing. It'd be hard, don't get me wrong, but it would be great to do. Question, Isabel.
So if we did that, then it wouldn't pass the Smith test?
Well, right, because it wouldn't be the tree we were expecting.
Okay.
If you did an AVL, if you made it AVL, set the AVL properties, the ones we were expecting are not AVL, so it would break it. That's all.
But we'd still get.
Well, you would submit both files. Basically submit both files, and you'd say in your README, hey, I also did the AVL, and we'd look at it and go, wow, you're amazing, and give you extra points. So, OK? All right. So that's the left, left, right, right. That's what we call the easier one, although the other one's not too hard. But here's what happens. We looked at the inserting the other day. Here's what happens if you try to do a single rotation on a left-right insert or a right-left insert. K2 is now out of AVL-ness, right? 1, 1, 2, 3. OK? So K2 is the one. What would we normally do to K2? Because it's too heavy this side. We would rotate it which way, Alexandra? We would rotate it to the right. Let's try that. If we tried that, we would grab on a K1 and pull it up. And what would happen is K2 would be here like this. And because the Y subtree is bigger than K2 and less than K2 and bigger than K1, it would end up on this side of K2. And look what happens. 1, 1, 2, 3. It doesn't work. OK, so we've got a little bit of a problem here. All right, not that hard to fix. What we need to do is this double rotation idea. OK, we have to do this thing called a double rotation, which I like to think of as two single rotations. OK, that's all the difference is. You will see when we do it that it's really not that hard to do. It's just two single rotations. OK, what we can do is we can say, fine, break this subtree up into kind of its components. OK, and then we'll see what actually happens. So if we take Y and we break it into its components, and we actually add another node in there, OK, watch what we can do with this. We can now, instead of just rotating K2, eventually we will. That's the second rotation. But the first thing we need to do is take K1 and rotate it. This is going to sound weird, but we're going to rotate K1 that way so that this thing becomes as if it was a left-left. And then we can do a proper rotation to the right for K2, and it will work out. So basically, you want to rotate K1 to the left. That will swap these guys over here. And then you rotate K2 to the right, and it actually works out just fine. OK? What would happen if we grabbed, let's write this on the board. By the way, I got a giant new piece of sidewalk chalk, and it's awesome. This stuff is great. This is like what teachers think of this stuff, I guess. OK, so if we've got this, we've got K2 and K1. And can you see it OK? The color's OK? OK. All right. That would be terrible if it wasn't. OK. And then A, and then B, and let's see. I already screwed it up. Hold on. K1, and then K3, and then B, and C, and D. Did I get that right? OK. All right. So if we're going to rotate K1 to the right, which one do we grab onto? K1's going to rotate to the right. So which one do we have to grab onto? K3. We grab onto K3. The K1, K3 stays the same. Everything on the left, or everything above it, stays the same. So I'll just write that down first. K2 and D. OK? And then we have K3 will come here. And then K1 is going to be here. And we then have K3 has still got C bigger than it, C. OK? And then K1 is going to still have A smaller than it. And then notice B is bigger than K1 but smaller than K3. So it should go like this. Now we're halfway done. We've done a single rotation to the left of this. Doesn't it now look like we've got a left subtree of a left as regard to K2? And now we can rotate K2 this way. Which one do we grab onto to rotate K2 that way? K3 again. So now it's going to be K3, right? And then K2 is going to be here. And then D is still bigger than K2. And C, which is bigger than K3 but less than K2, is going to go here. And on the left of K3 is still going to be K1 and A and B. OK? And now notice, 1, 2, 1, 2, 1, 2. Everything works out just fine. OK? So it ends up being like that. Sorry, I didn't get it oriented quite right. But that's how it ends up being. And it's fine as far as AVL quality. But you have to do those double rotations or 2 single rotations if you have this situation. Question?
Now, you mentioned that this won't be on the project for this week. I was curious, do we have to know how to code this for the test?
Yeah, good question. You will not have to code this. We'll talk about coding it a little bit at the end of the class, but it's just saying kind of what you have to think about. It's a little bit like intense. And then I've got a dirty little secret about it that I'll tell you at the end. OK? But yeah.
Isn't this very processing heavy?
Well, we'll talk about that in about 10 minutes. So think about that. Think about the question. Hold on to your question. The question was, is it processor heavy? Hold on to that question, and we'll talk about that, because that's a very good one. Winona?
So because it's the left subtree right node that has a problem, you rotate left first and then the right? Or is it not?
Yeah, no, that's absolutely right. Because it's the right subtree of the left child, you rotate left. But I just like to look at it and go, what happened here? We put something over here, and that's a left-right. And we really wanted it to be a left-left. So let's make this stuff balance this direction. We have to shift this way. I mean, it just you can think of it either any way you want, but you'll get used to it once you see it a few times. OK? Yeah.
So is one way to think about it kind of ignoring K2 and D and just
Yep.
basically thinking of K1 as being the root in a like
Yes. You can.
and then balancing
Right.
that and then balancing the greater structure.
Yeah, you can think of it that way. You can say, OK, I'm balancing the greater structure. But keep in mind, this one's not out of AVL. Right? Look, 1, 2, 1. It's OK. So you can't think, oh, this one got messed up.
Yeah.
It's not that this one got messed up. But yes, this is the one you deal with first.
So
Yeah.
it's not that it's messed up, but like you're kind of like balancing it in parts.
Yes, sure. You're balancing it in parts. Yeah. We'll see some examples here, and you'll kind of start to get it. But if you don't get it, that's all right. Practice it. I will ask you something like this on the test, being something, for instance, I'll give you a real tree with nodes, not triangles and things. I'll give you a tree with nodes and say, insert the following, and then balance it. Tell me your steps, and then balance it. OK? That's all I'll ask. OK? It works the same for a left subtree of the right child. So if K1 ends up being out of true, this is the left subtree of the right child. OK? You do the exact opposite. Which one do we have to rotate first, and which direction? K3 needs to rotate. Yeah, careful. K3 needs to go this way. Right? And then once that happens, then we can rotate K1 that way. And it ends up coming out like that. OK? Make sense? We'll see some examples of this. OK? All right. In fact, we will right now. Let me see. Let me erase some of this. And then, all right. Let me write all these down. 16, 15, 14, 13, oops, 12, 11, 10, 8, 9. And that was after we did 3, 2, 1, 4, 5, 6, 7. Did I get all that right? I think so. OK. So let's go back to the web page that we had the other day. And we will make it nice and big. And what I will do is I will speed it up so that we can enter the first ones first. We're just basically going to start where we ended up yesterday. 3, 2, 1, 4, 5, 6, 7. 3, 2, 1, 4, 5, 6, 7. OK, that's where we ended up the other day. Oh, let me make it a little bigger. You guys see that now? Hopefully. OK, so now if we add 16 to this tree, if we add 16, I'm going to slow this one back down. If we add 16 to this tree, it will go where? To the right of 7. And do we have a problem? Let's make sure. 16, let's see. 1 and 0 is fine. 1, 2, 1. 1, 2, 1, 2, 3. We're OK. And the left side can't, or the left side can't be different, so we're good. OK? All right, so that's fine. And then now we're going to do 15. And where's 15 going to go? 15 is going to go to the left of 16. And are we going to have a problem? Where are we going to have the problem now? 16 is fine. 1 and 0. 7. 1, 2, and 1. So we're going to, or I should say, or 0 rather, and 1, 2. 0 and 1, 2. Yeah, so that's it. Now, can you tell what kind of rotation we're going to have to do? It's going to be a double because we have gone in the left subtree of the right child. OK? So what happens first here? $16 gets rotated to the right. And then we're going to rotate 7 which direction? To the left. OK? So really, this is going to become, it's going to become 7, 15, 16. And then it's going to become 16, 7, and 15. Now, the way the animation does it, it says a double rotation. Watch. When I do this, it'll say, right here, it says double rotate left. It's a little hard to read from the back, but it says double rotate left. And it will now actually go 7, and it will grab 15 immediately. And it's a little hard to, like, if you're not used to it, you'll go, what is it doing? Watch this. Boop. Right? I'll show it to you again. Step back, step forward. Step back, right? Step forward. Now, that's doing a double rotation, but doing it in one step. I wish they had coded this so it does the first animation, the first one like first. But that is the same thing. Yeah.
Just curiously, if you wanted to make a function just for like a double rotation,
If you wanted to make a function for double rotation, yeah.
just pass in the three pointers to each node and just take the middle value on top and just do left and right pointing.
Can you? Well, yeah. So your algorithm is going to need to be a little more advanced than that, but it's going to be basically that idea. You pass in. You would probably just pass in the one that's the. You would be at the one that's got the issue, and then you'd need to know. OK, I need to go to its child and see if it was a left and right, et cetera, et cetera. You need to do a little bit of computation. So it's a little more subtle than that, but it's you're on the right track. Definitely on the right track. OK, so that was 15, right? So let's put 14 in there. Let's see. Yep, I got to skip forward. There we go. 14 goes in there. And 14 goes to the right of 7, right? So is there a problem here? Let's see which one has a problem. Does 14? No. Does 7? 0 and 1. Does 15? 1 and 1, 2. Nope, they don't differ by 1. How about 6?
Yeah.
1, 2, 3, and 1. Right? So that's the problem. So we're going to have to rotate 6. Now, which type of rotation is this going to be? Why is it a double? The left child of the right, or yeah, the left subtree of the right child. OK? So 6 eventually is going to have to rotate this way. 15 first rotates which way? This way, right? OK, to do that, 15 goes, so 7 goes here. And then it ends up being, let's see, 7 here. And then guess what? 14, 15, and 16 are all bigger, right? Than 7. So it's going to end up being very heavy on the right. But then when we rotate back, everything kind of works itself out. OK? Let's actually draw this one while we're thinking about it. Might as well. OK? So let's see. I can barely see over there. It's going to be, I'm just going to draw from the 6 down, because the rest isn't going to matter. 6, well, it won't matter. Yeah, it won't matter here. 6, and then what's over here? 5? OK. And then actually, you'll have to read this off, because I cannot see the board on this side. This one is going to be 15, and then 7, 16, and then 14. OK. First things first, we're going to rotate the 15 this way. So we grab the 7 and we bump it up. I ran out of space over here. Let me do this over here. OK, so we're going to grab the 7. So it's going to be the 6 is going to remain the same. And then the 7 is going to be here. OK, and then the 5, of course, is going to stay the same. So the 7 is going to be there. And then it's going to be, we don't change the 15, 7 there. So what's going to be to the left of 15? 14. And then what's going to be to the right of 15? The 16. So that's step 1. OK? And now we've got it so that, of course, as far as 6 is concerned, it looks like a right. And so now we can rotate the 6 this way. And we'll do that. Which one do you grab? 7 again, right? So it's going to be 7. And then the 6 is not going to change. So it's going to be here. 5. And you're thinking to yourself, oh, this is going to be way out of alignment. It's not. You'll see. Right? It's going to actually be OK. And then for here, nothing's actually going to change on this side, right? 16 and 14. OK? Is everybody OK on this one? 1, 2, 1, 2. That's good. 6 is 1 and 0. That's good. 15 is 1 and 1. And everybody else is good. So when it happens here, let's step on this one forward. OK, it's going to go back up. And it's going to walk up. And it is going to get to 6 and say, oops, it's a double rotate left. This one will, if you want to think of it this way, I'm happy. But sometimes it takes it's like too many steps for my tiny little brain. 6 grabs on directly to 7. And then everything, the magic happens. OK, watch. There we go. Step back, step forward. See how that works? Again, the double rotation part is what I think you should concentrate on, doing 2 rotations. OK? All right. So let's do a couple more. Let's see. That one was 14? 13 now. OK. Oops, play. There we go. 13. Insert 13. OK, I'm just going to let this one go. 13 is going to do what? Yeah, let's see what happens. Where does it need to change? The root. Oh, we better look at that one, right? Let's just step forward. Let's see. Can I step back on that one? Step back. Step back. There we go. OK, we put 14 in which? So we started, or sorry, 13. We put 13 here. This was OK. This was OK. This was OK. This one's not OK. Which rotation does it need to be, single or double? Why is it single? Because it was of the right child. It was the right subtree. Even though 14 ended up going this way, it was the right subtree of 7. Yeah? So it's a single rotation, meaning you grab onto 7, right? And then 4, and then the 5 and 6 have to go to the right of 4. And that's what ends up happening. OK, so when we do that, there you go. OK? And that solves the problem. OK? All right, let's see. That was 13. So this is 12. Only a couple more on this. I just want you to get a feel for it. And you can tell me which ones these are going to be. 12. Can you tell already? I can tell already. If you do this enough times, you go, oh, 14's out. Single rotation. Right? Why was it a single? Because it was a left-left according to relative to 14. OK? And then that was 12. So then 11, insert 11, and 11 goes down. And let's see what happens here. That one's OK. That one's OK. That one is not OK. But I'll step back. Hang on. Step back. That one was according to 15, which was the one that was out. We put it down on the left. So it's just a single rotation. I think I screwed up and didn't put any more double rotations in here. But that's the way it goes. OK? And notice it's not such a bad thing to do these rotations. The whole left side of the tree didn't even change. And you only changed everything below the one that was the problem. So when you're thinking about if it's a lot of work, well, it's some work, but not too much. OK? All right. So that was that 11. Let's do the other ones anyway. Might as well finish them up. 10 goes in here. And insert 10. And this one's another one. You can tell immediately what happens. It's got to be 12, right? So 12 needs to be the single rotation and being like that. And notice this is keeping it pretty well balanced, which is exactly what we want. We love that about this. OK, and then that was 11. That was 10. Yeah, this is 9. Nope. 8, 8. See what happens when we insert 8. I'll pause it on this one to see if we can figure it out. So 8 goes here. Is that going to cause a problem? 1, 0, 1, 2, 2 and 1, 1, 2, 3, 1, 2, 1, 2, 3, 4, 1, 2, 3. No, it's not even going to cause a problem. So everybody's going to be good. All right, and then finally, 9 is going to get inserted, and see what happens here. 9 is going to be there, and who's going to have the problem? Careful. 9 is OK. 8 is 0 and 1. 10 is 1, 2, and 0. So it's the one with the problem. And what kind of rotation is it? Oh, careful. It was a right subtree of a left child. So it's a double rotation, right? First thing you do, rotate 8 this way, which is easy. Grab onto 9, and it goes 10, 9, 8. And then rotate 10 to the right, and it goes 8, 9, 10. OK? And double rotation, and ba-da, like that. OK? Look at this page if you want practice on this stuff. You can do it for the next week if you want to practice it, all on your own. OK? All right. I think we've beaten that one to death. So the question came up, how do you code these things? Well, it's a little bit tricky. It's straightforward in that you know what you have to do. In other words, you can look at a rotation and you can figure out what has to happen. Okay, there's nothing magical about it, right? It is definitely easier recursively than not recursively. The recursive solution is never the fastest because you've got all that overhead of recursion. But it's generally much more clear than if you're going to do an iterative solution. That one can get really ugly. By the way, that's another good above and beyond. If you wanted to change the project to be iterative, you'd get lots of points for that because that'd be hard. But anyway, to insert, first we already know this. Do a normal BST insertion. And then if the height of the subtree doesn't change, stop, and you go back up the subtrees. If the height does change, you do the singular double rotation and update the heights. And you only need to do one rotation, and it'll work fine. OK? If you really want to look at code or practice it, you can find an example online, somebody who did this. OK? Now, you want the dirty little secret about AVL trees. You probably will never see these in real life. They're kind of like the linked lists of trees, right? In the sense that there are better balancing trees that are harder to understand but are better. So people normally take the time to code up the better ones. If you take Comp 160, which is algorithms class, you will talk about a thing called a red-black tree, which is very similar. But not only do you have to worry about rotations, you also have to worry about the color of the nodes. You actually go and you make nodes of different, like red and black nodes. And it's easier to teach AVL trees. So I wanted you guys to see those so you get the idea of rotation without the other stuff. OK, when you get to algorithms, you'll get plenty of practice on the other stuff. OK? All right. Other questions on AVL trees? All right. Good. We've beaten that one to death. The other kinds of trees you might see that are balanced, a thing called a 2-3 tree, double A tree. I don't know what that is. AVL trees. We talked about red-black trees is the one you'll see more often. I don't know what a scapegoat tree is. A splay tree and this thing called a treep, which sounds like heap because there's a heap structure. And I suppose this is similar to that. OK? So there's other balancing type trees. We will talk about other ones in other classes. OK? All right. There's some more reading to do, and you can do that. All right. Let's go on to a couple other topics. We're going to stick with trees for a few minutes here. But then we're going to talk about this thing called a prefix tree, otherwise known as a trie. Now, I think the naming was unfortunate. Because it looks like, wouldn't you sometimes maybe want to pronounce that tree? Like if you're German or something, you'd pronounce that tree, right? Well, you don't want to call it a tree. It is a tree, but it's a special type of tree called a trie. The guy who invented it actually pronounced it tree, even though he spelled it this way. Who knows why? Right? I don't know. But anyway, these are tries. We will call them tries. You can also call them prefix trees. We'll get into what those are in a few minutes. OK. Now, we talked a little bit about the asymptotic complexity of a binary search tree. Let's revisit that for a few minutes. OK, the asymptotic complexity for a binary search tree. A straight up regular old binary search tree with no balancing in there. What's the worst case asymptotic complexity for find min and find max? Linear, right? Because it could look just like a linked list. Okay? So the asymptotic complexity of find min and find max is linear. Same thing with contains. Okay? But let's pretend we have a balanced one or a mostly balanced one. What's the average asymptotic complexity going to be for find min and find max? Logarithmic, right? Same thing for contains. Because remember, contains, you just have to go like one side or the other, depending on what your relationship is to the current node. And you basically, if it's balanced, you're going to break the tree in half, 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 again and again and again. Right? So that's if it's balanced, we can do that. So logarithmic, logarithmic, logarithmic. Insert is logarithmic. What about remove? We've got all these cases here. Are we going to change the asymptotic complexity with all those extra cases for remove? What do you guys think? Ask your neighbor while I erase something. Talk to your neighbor and say yes or no about that. You don't have a neighbor today, Kate. Too bad. What's that? I know, I guess so. All right, what do you think? Who thinks we're going to change the asymptotic complexity of remove because of all those extra cases? Raise your hands. A couple people, 1, 2. Nobody does? The question? That was you talking about for the last 3 minutes. Remove, are we going to change? So all these other things are logarithmic. And now we're removing, and remember we have to do special stuff with remove. We have to figure out if it's the no children, or if it has one child, or if it's 2 children, then we have to find the maximum of the minimum of the right child, et cetera. Right? So the question is, who thinks that remove is going to be more asymptotically, or have a worse asymptotic behavior than like contains or whatever? Raise your hands. Who thinks it's not going to be? Why are only like a third of you raising your hands? Like how? Some of you guys didn't, and then some of you did. OK, so first, one more question before I let somebody say why they think what they do. What's the first thing you have to do when you do a remove for some element? Find it. Right? Is that what you're going to say? Do you know? Yeah, you have to find it. So isn't it at least going to be as expensive as contains? OK, so it's at least going to be. So is remove going to be more expensive than contains? Yeah. Is it going to be asymptotically more expensive? No. Why not? Somebody who yelled out no. Do you know?
Because they act as constants.
Yeah, they act as constants in the sense that you don't have to do anything related to all the nodes anymore. Right? Let's say that we were removing, I don't know, 15 from this tree right here. OK? We go from here. We have to find 15. OK, we can say that that's asymptotically logarithmic because it's a balanced tree, right? Asymptotically logarithmic. But did we actually go all the way down to the bottom? No. We may have to go down to the bottom. In fact, if it's a node with 2 children, you certainly do, right? Because you need to find the minimum of the right subtree. But isn't that just completing the logarithmic property of it here? It's not adding any extra logarithmic complexity here, right? So you do have to go down there. But yeah, as you're saying, it's only like a constant extra amount of work. So yes, remove is still asymptotically logarithmic. It's slightly worse, but we don't care about the constants in this case. We generally don't care about constants when we're talking about logarithmic behavior or asymptotic behavior. OK? OK, so now that you've got that going in your brain, so yes, remove all of these functions are logarithmic for a balanced tree. Does inserting into an AVL tree change the complexity of the operations? Isabel?
I would say yeah, because you are not only trying to find it, but then you have to go back up
Okay, that's a very
and deal with different
yeah. So that's a very good point. So yes. So if you're adding to an AVL tree, remember, let's say we added 13 to this. We go down and we go find where 13 goes. We put it in, right? And then we climb up again, and it turns out that nothing has changed in this one. This one looks okay, right? Oh no, yeah, this one's okay, right? But didn't we do logarithmic down and then another logarithmic back up? Okay, so that's how many logarithms? 2 log n. What does that really become? Do we care about the 2?
But given you're not having to balance that tree.
OK, if we had to balance that tree, let's say it adds another 3 operations to it. Isn't 3 plus 2 log n still log n? Right? So yeah, so you're doing more stuff, but in the end, it's all more constant behavior. Yes, it's twice as long, and it takes twice as long to insert into an AVL tree as it does to insert into a binary search tree, on average, right? But twice as long for a billion elements, yes, it's twice as long, but over the course of, it's not 2n times as long, or it's not any other component of n. It's only twice as big, right? So logarithmically, we ignore all these constants, and it's still just logarithmic behavior. OK? Yes, it's twice as much, and it could be 20 times as much, depending on what you're doing, right? Not in this case, it wouldn't. But even 20 log n is still log n, because we don't care about these constants. Yeah?
So at some point, can't the constant get big enough where it would really, it's not just a constant anymore, it's affecting it by,
Yeah.
by such a big value
right.
that it's becoming.
Yeah. That is a very good question. The question was, hey, look, can't the constant ever overwhelm this other stuff? It can when we're talking about small amounts of things. So yes, in some cases, we would consider the 20 being important if it was 20, but not if there's a billion numbers here. We don't care about that. It doesn't overwhelm this if we're talking big numbers, which is what we really care about when we're talking asymptotic behavior. Okay? If you ask Professor Ben Hescott, who does this stuff for a living, right, he will say, I could care less about any constants ever in my entire life. I don't care about them. Right? Because he just deals with these kind of issues of big, big, big numbers. He doesn't ever deal with the little stuff. Now, if you're talking about small trees like what we're dealing with, sure, 20 times longer is going to all of a sudden become apparent. But if you're talking about a 20-element tree, you know how fast your computer can handle that? A millisecond? No, a microsecond? A tenth of a microsecond? You know? I mean, it's so fast it's not going to make a difference. If you're talking about millions, it'll start making a difference. But 20 million versus a million to you seems like a lot, but in the big picture, it's not huge. Good questions. All right, so all of that is saying that AVL trees still logarithmic behavior, even though you have to even though you have to go up and down the tree twice. OK? All right, good. Now, enough about these things. Let's talk about these ones, which are, like I said, one of my favorite type of data structures. These things called tries, again, not the best name in the world, but you'll get used to it. Tries are known as prefix trees. We will see why in a minute. But here's the kind of the setup. You guys have cell phones, right? OK. You guys know Bruce Smollett? You guys seen? I shouldn't say this on video, but have you guys seen the website? It's like CS students say. You seen that website? It's like stuff that you guys say about professors and about the department and about Halligan Hall and how it smells after a Comp 40 assignment's due and all that. Right? It's like, whatever. You guys know what that? Well, somebody put on there about Bruce Mollet that he's something like he's like a brilliant programmer, but he still carries around a 1990 flip phone or whatever, right? And he does. He carries this like, whoop, he has this flip phone, and it's got some old ring on it I haven't heard since the 80s or whatever. But anyway, most of you guys probably have like actual smartphones, right? And your smartphone, when you're typing a text message, and you're going along in the text message, and it does autocomplete for you. That's kind of neat. Sometimes it gets it wrong, but sometimes it does autocomplete for you. And did you ever wonder how the phone knows how to complete your words? Yeah, I always wondered that, right? Well, one way to do it happens to be using this object called a trie. OK, so it's kind of neat. And this is like a real life sort of thing where you'll actually figure out like some of this. Now, one of the other reasons we like to learn this is because for the final project, it's probably a good idea to use one of these on the final project. So pay attention now, and your final project will be less hard. Not easy, but less hard. OK? Let's say that we wanted to search a dictionary. OK? And this is kind of what you're doing when you're doing autocomplete or some other word-based thing. You guys even know what dictionaries are? Like they're the paper ones, right? What's that?
Dictionary.com?
No, not dictionary.com. Paper one, right? So we're looking for, let's say we want to search through a dictionary. We could put all the words in that dictionary into a binary search tree because, as we said, binary search trees don't necessarily have to be numbers. In fact, most of the time, they're not just numbers, right? There's something else that you can compare against. And you can compare two words alphabetically, right? You can say one is greater than if it comes later in the dictionary than another word. OK? This is what it might look like if we put a bunch of random words in here. OK? It might look like this. Notice that fire is earlier in the dictionary than red. So it actually comes before it. So this is like greater than fire. Like red is greater than fire, right? Pit is earlier in the dictionary than red, but after fire, et cetera. It's just a binary search tree. And we could put them in here like this. And what is it going to take asymptotically to search for something in this tree? Logarithmic if it's balanced. If it's not balanced, it can be up to constant behavior, which is not so great, right? But we could do this. And this is a legitimate way. And if it's balanced, that's not so bad, right? But it's still this n behavior. It's not n factorial. I just put exclamation point to say, oh, no, that's bad, right? The behavior is still order n if it's not balanced, right? And normally it's logarithmic, right? But there are a lot of words that actually share prefixes, which is kind of cool, right? Especially in English, we have lots of words like fire and fish that share the first two letters. And we've got cow and corn that share the first two letters, and so on. Lots of words like that. Yeah?
Does it have to be binary?
Does it have to be binary?
Good pointers or whatever?
Yeah, good question. We'll get there. Right? We could make, that's a very good question. Does it have to be binary? It doesn't have to be binary, as it turns out. Other languages, I'm not sure how many other like non-Latin based languages have all these. Like Chinese doesn't have like characters like that make up individual words, but don't Chinese characters share strokes and things? I suppose, right? So that's maybe in some sense maybe a sharing idea. So a lot of things can fit into this model, but it works particularly well, at least for our case, in English words, OK, that share these things. OK, now, to your point exactly, you can do better than log2 if you don't limit yourself to a binary tree. We could have a ternary tree, which means 3, right? And we could just have like 3 nodes, and then you're not going to have to do log2 behavior. You've got log3 behavior, which is actually better than log2 because you can split things into 3 instead of 2. It's kind of nice. You got a question or comment? Could you do log 26? You could. Why 26? The alphabet. OK. Hold on that word. Hold on that for 1 second. OK, that's very good. OK, we could search log3, but you're absolutely right. First of all, the problem with binary, the good thing about binary tree was we were limited to 2, and it made it easier. We had a left and a right, and that's all we need to think about. If we do like as many as we want, we have this thing called fan out, which is a problem where you have multiple nodes going out, right? But words are limited in what sense? Yeah, words only have letters in them. Now, some words, I mean, if you're just talking about lowercase standard English words, there's 26 of them, right? But all of a sudden you get into like, let's say there's words with accents on them, on letters, or an enya or something, right? Then you've got other issues, and you might have to make this, like 26 doesn't quite cut it. Yeah?
I was just going to say it's 28. You need A, E, and apostrophe.
Right, you need some other one. Well, apostrophe is not, you could limit the words to not apostrophe. You could just take out all punctuation or whatever. But yeah, you've got other issues. And if you want to do numbers, you've got digits. But if we concentrate on just lowercase letters, we concentrate just on lowercase letters, then there's only 26 of them. And we could, if we wanted to, make every node have 26 children, which is a big fan out, but legitimate. And we could do something kind of cool. Yeah?
How many ASCII characters are there, not counting like...
How many ASCII? We'll talk about ASCII in a few minutes. How many different characters? Well, there's 127. And then there's actually 256 if you want to expand it a little bit more. And then there's infinite if you want to go to like things like Unicode and all that. So you have to be a little careful. But for many cases, we can at least find some subset that will get lots of words, like for instance, for autocomplete. OK, we can find lots of, like a small amount of subset. For our purposes, we're going to limit it to 26 children per node. OK, and we're going to retool our tree. Instead of dealing with the words themselves, we're going to deal with just the letters in each word. Okay? And we're going to base the new structure on those prefixes. Okay? So watch what happens here. I know this looks a little strange, but take a look at what happens. We've now said break words into their individual characters. And know that lots of words share these prefixes. Cow and corn share the first two letters. So this is what our new structure looks like. C is the first letter in both. And its child for both these, its only child in this case for both of these words is O. And then we've got it where it breaks up into differences, because they're not prefix anymore. They don't share any more prefix after C and O. And so corn goes this way, because R is now a child of O. And W is a child of O. And you can have 26 total. And for the R, now you've got an N there. And for the O, you just have a W there. This is called a trie. Winona.
But what if you have a word that's also a longer? What if you have a word in which the same four letters of, like let's say there was a word cowbell. How would you fit that?
There is a word cowbell. That's a legitimate word, right? I think. Let's figure it out. So I wrote a little program to do this. Let's see, where is it here? Comp 15, lectures, day 9, try. OK. So I wrote this little program to do this. It's kind of a fun program to write. And you will play around with this in lab, this actual program here. It's kind of fun. You'll actually interface your lab with the web-based thing. So I think it's kind of fun. But let's add some words into this. So what did we add before? Cow and corn, right? There's cow, and corn goes like this. Now, you said cowbell, right, Winona? OK, so if we had cowbell, let's just think before we even do this. By the way, the root of these things is like no letter. We don't want it to be a particular one, because not all words start with no, like a particular letter. So C-O-W, so for cowbell, C-O-W, and then what happens here? Add a B right under B-E-L-L. So let's see what happens. OK, cowbell. And now it looks like that. And let me make it a little smaller. There we go. OK, now, what do you notice about the way I've put extra? What other information did I put in this one? Color. So guess what? If we're going down here, tell me when a word stops. And tell me when another word stops. Right? So you see how in this case I put colors. On the other one, I actually denoted it with asterisks. I didn't on this one. Next page I did. Asterisks, right? Like that. And so you do have to tell where the word ends, because you're absolutely right. Some words are completely fit into other words. OK? Yeah, Isabel, you had a question.
Oh, I was just going to say, like, by marking it with something.
Yeah, by marking it with something, right? So we can do that. Let's do this. Let me just recreate the same one we have up here. Let's see. We have cow, corn, day, fish. Let's see. Cow, corn, day, fish. And let's see, what else do we have? Fire, pits, red. Fire, pits, red. And what else? Let's see. Pits. Oh, we have pit as well. Oops. Well, now we have pie, too. Did I tell you guys about pi the other day? Yeah. about the contest I have to do? Somebody sent me a little song that's the first 200 letters of pi, or 193, so I'm really psyched. All right, let's put pit in there as well. We'll say pi is a word, and pit. And sand and snow. Sand and snow. OK. All right. So you can see in here where the words end by we mark them. So you definitely have to mark the ends of words. OK, if we're going to search for a word, how do you think we're going to go and do the actual search for a particular word to see if it's in our try? Somebody has an answer in a little bit. OK, go ahead. Oh, go ahead. Zoe.
Say like letter by letter each time.
Yeah.
If you get a match, you would move to the next letter.
Yeah, let's search for one of the words in here. Which word do you want to search for? Fish. OK. So if we're searching for the word fish, we start up here, and we see if that node has a F child. Right? There it is. And then we see if it has I, and then we see if it has S, and then we see if this one has H. And then what do we do? Well, careful. We check what? Is it a word marker? In other words, in our case, is it red? And if it is, then we say, yes, we've got fish in there. OK, let's search for SA. See if SA is in here. Does this have an S child? Does this have an A child? Should we return true? No. Why? Not red. OK, you get that? Let's search for sands. S-A-N-D-S. S-A-N-D. And then does D have an S? So what do we return? False. OK, do you see how that? So searching's pretty easy in this. Right? Yeah, Isabel? Give me another word to add.
I was thinking like if it was like if sand was actually like a subtitle of.
There are no subchildren like that unless they share prefixes.
Like for example, cowbell, like the word bell.
Yeah. Let's do that. Let's put cowbell in there. Cowbell goes down there. And where does bell go? Starts its own B, because there is no B yet. And there it is.
Okay.
Right? And so now it's over there. And see, cowbell and bell, they don't share a prefix. You could come up with what's called a suffix tree if you wanted to. But it's a little weird. And
So
you
like,
could do that.
you wouldn't necessarily, so bell would be in there twice.
Well, the B-E-L-L letter range would be in there twice, sure. But if you were doing a binary search tree, you'd have cowbell and you'd have bell in there as well. So there's nothing changing in that sense. Who wants to add some other words? Nobody? OK. How about this? Supercalifragilistic. I don't know if I can spell this. Expialidocious. Close enough? OK. All right, there it is. Oop, yeah, there we go. Supercalifragilisticexpial. Right? And it goes all the way down here, right? And that's it. So we've added to our tree. I actually did add one here which says add a lot of words. I think that works. Takes a little time. Then it adds lots. And I told you it was lots. Right? Need a bigger screen. And then my little algorithm to print it out, I mean, it does get a little ugly when it gets over to these. But it adds lots and lots of words. OK, now let's talk about some properties of tries. Yeah, question?
If you had the word cowbell in your function and you wanted to remove, is there a remove at all?
Is there remove at all? You know, we don't really talk too much about remove, only because it's not really used that often. But yeah, you can remove things and you would have to just bump everybody up properly,
But what if you
right?
wanted to remove cow and not cowbell?
Yeah, if you wanted to do cow and cowbell, you'd have to first traverse down and make sure there's nothing after that. And then if there is, you just take out the word marker, right? I mean, that's kind of the idea in that sense. But yeah, we're not going to worry too much about removing words from this. But you can do it. It's just a little more work.
Word markers just seem like a sort of like a struct or something that like so that the nodes contain like a certain.
Yeah, let's talk about that struct. What a struct for would be. You would have a node, and this, by the way, this is pretty easy to do recursively. You would have a node, and then the node would have a value, which would be the character, right? And then its children would be, let's say, one good way to do it is an array of 26 letters. Okay, an array of 26 characters, right? And then a word marker. And the word marker is either true or false, right? And that's it for your node. You don't need anything else, right? You need the node itself. Inside the node, you need a character to say what character it is, and then you need to have the actual children, which are 26 long. Okay? Could do it with a linked list if you didn't want to keep all those 26. The problem with linked lists is it's slower in the sense, it's always slower, right? But it's slower in the sense that, let's say you were looking for the word Z, 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 right? And you had to go through and you go, so you go Z, and then you look for all through the whole linked list of the subchildren to Z, and then you look for the whole, it gets a little slower. OK, but let's talk about some of the properties of this. OK, the reason I like this is because of some of these properties. The cost of looking up a word or prefix is fixed. You never need to go deeper than the word length, right? For our tree, if we're searching for corn, what's the most we have to go down the tree? 4. You don't have to go down, 52 times before you get to corn. You have to go C-O-R-N, and that's it. There aren't too many words like supercalifragilisticexpialidocious that have 20-some letters, right? And even 20-some letters is only 20 times down the tree. It's not like you're going thousands of times down the tree, right?
And if it was just holding the words, you would be going.
If it was just holding words, you'd have to be logarithmic in relation to the number of nodes, which isn't bad, obviously, but it's not.
But it's not as good as
It's not. Well, let's see what this is. Does it matter that corn is in here and then there are 5,000 other words, or 50 million other words? You still just have to search down. You go C, and then it doesn't matter what's in the whole rest of the try. You go down to the next letter, and that's it. So it is not based on how many words you have in there. It would be kind of bad if the way Apple did it on your phone was they said, OK, every time you're typing another letter, we're going to search through 1 million different words, right? It just would not be very efficient, right? And you'd yell at Siri and whatever. I don't know. Turns out when you yell at Siri, I just found this out. I don't know why I'm surprised. When you yell at Siri, it gets when you talk to Siri or Google Now or whatever, it saves everything you say, and then somebody listens to it at some point. And it's only for quality control and for whatever. But when you tell Siri to go F off or something, that somebody reads that and or listens to it rather. Anyway.
Sometimes it's best is, I was reading this article about Siri and autistic children.
Oh yeah, that's a great article. Siri and autistic children. It's really cool.
And it's about how they basically befriend Siri because
Yeah. I think the article's called My Son's Best Friend is a Phone or something. And you think that's kind of sad, but it turns out to be a very beautiful story. Turns out, yeah. New York Times, I believe. Good. OK. So anyway, not based on vocabulary, which is nice. You don't need to balance these things. There is no balancing here, right? There's no such idea that you can have some part weighted more. And I mean, the only way that could really happen is if you happen to have you're only doing the A's, right? Everybody's going to be A, right? But other than that, there's no other balancing. You don't have to actually balance this. It's just based on the length of your word in that case. So the max depth is based on your word length. What's the complexity of this? Of searching for a word, I should say. What's the complexity of searching for a word? Somebody else who hasn't answered in a little bit. Somebody in the back corner there. You guys are being quiet today. Complexity, what do you think? Length of the word. Isn't the complexity, if you want to find out how long a word is, don't you have to do that many searches down? Maximum? That's the complexity, absolutely. If it's the length of the word, what can we simplify that to? Constant. So actually, you can, again, exclamation point because this is awesome. You can actually change the complexity. The complexity is now order 1. We will actually be more specific and say that it's order the length of the word. In the big picture, that doesn't matter. It's still constant. But if I ever ask you, what's the complexity of looking through a try, you should say it's order the length of the word. Just because it's a little more detail and,
unless try is about words.
Well, all right, if it's some other type of detail, yeah. Or some other type of try, yes. But mainly it's going to be letters. Okay? Somebody asked after the other class, could we have a try that was made out of, like for numbers? Like where each digit was a different, you could. It's a little wacky, but you could. I think you'd run into trouble with it. Wouldn't be the most efficient thing in the world, but it'd be all right. We do ignore some things when we talk about complexity. When you're comparing to see if you're at C, remember the computer has to do an actual comparison. It has to say, is C equal to the node that, or the letter that I'm at? Is O equal to the letter? So that's something else we're kind of ignoring when we talk about the complexity. But we ignore that a lot of things when we talk about complexity. So anyway, bottom line, this is considered a constant behavior data structure, which is great. Okay? And more specifically, its behavior is order the length of the word you happen to be searching for. Okay? All right. What are some downsides to a trie? Well, so we do have to deal with this idea of 26 different characters if you're just doing lowercase. But if you add like apostrophes, and if you add periods, and if you add ennyas, and if you add all the other little characters you could add, yeah, that can start adding up. You're not going to be 26. What if you had uppercase letters? How could you deal with uppercase letters in these things? What's some of the way? What do you think?
You could just have a marker, kind of like you do with at the end of the word.
Mm-hmm.
You could have a Boolean marker that says whether the letter is uppercase or not, and use like the to lower function that we were supposed to do in Problem 11.
Oh yeah, you could use it. So you could
like,
say have a marker.
Interpreted everything in lowercase, but you had a marker that noted whether it was uppercase.
That's not a bad way to do it. Isabel says you could interpret all the letters as lowercase, but have a marker saying it's an uppercase. It depends what you're trying to search for, right? What if you need to know, what if you need to know if every other letter is uppercase or something? It's a little trickier, right? But you can do that sort of thing. Yeah?
I was just going to say you could also, because assuming we're just talking about upper and lowercase letters, every character in that is an ASCII, which converts letters into...
Yeah, we'll talk about that in a second. Yeah, we'll talk about that in a second. Good. You were going to say something. Right, the first letter might be uppercase. Now, Apple and Google and Android phones or whatever, they're smart enough to, if you start a word with an uppercase letter, generally they will give you they will try to complete it with the first letter uppercase. They'll try to change it to the first letter being uppercase or whatever. That gets into a topic called heuristics, which basically says, OK, this is not an algorithm that's true every single time. But most of the time, uppercase words, we want to give you suggestions that are uppercase or whatever. But it's not quite as well defined as this. But it's a great topic in itself. OK, but tries itself, because of all that extra space because of all the different nodes, you do run into this issue where, yes, we're compressing the trie because of the fact that we've got these shared prefixes. But because you've got so many different children, you end up expanding in that way. It turns out that for an equivalent binary search tree and trie, you generally will have the binary search tree will actually be a little bit smaller, as it turns out. Okay, depending on how you build your trie and so forth. But we do get some compression out of this. The biggest benefit is the speed of the search. Okay, it's not based on the size of your dictionary at all. Okay.
So basically, you would decide whether you wanted speed or.
Yeah, you'd make a trade-off between speed and size, maybe. Maybe they're roughly the same, but binary search trees are generally a little smaller in most cases. You can compress this a little bit more. Let's say that you have words that do share the suffixes like this, right? Day and, well, day is the only word here. But let's say sand and sand here. The last part of sand is A-N-D. And so you can actually, if the last part of the word does not have any other children, you could figure out a way to compress it into one node. Now, your node structure gets a little bit more complex in that case. You're going to have to keep a whole string or something like that. But you can compress it to some extent. OK, pit and pits. Uh-oh, now you're going to need 2 word markers. So it gets a bit more complicated. Gets a bit more complicated. But you can do this. Can we compress this even more? How might we compress this a little bit more? Are there any places that don't branch? Winona?
Like CO and corn and cow.
Yeah, why not? CO doesn't branch, so let's compress that. And FI doesn't branch. So we can actually do it even more and compress it like this. right? But again, you're updating or you're increasing the amount of logic you have to do, but you're getting a slightly more compressed tree in some sense, or trie in this case. Okay, so there's definitely some interesting things you can do with this. Remember the first week of class I said, first day of class I said, this course is all about like how to get a job at Google? All right, remember when I said that? This question, so I know people who, so there's one student, she's a senior now, she got an interview at Apple, which is awesome, just because she happened to mention on her resume, hey, I implemented a project using a trie. And the recruiter from Apple called her up and said, did you really use a trie on this project? And she goes, yeah, I used a trie. We learned about them in data structure. And the recruiter said, whoa, that's really cool. We want to interview you. Right? Because not that many people actually know what tries are, and not many people would know how to implement them. And they're kind of a cool data structure. So that's neat. Another student actually who was interviewing at Google. In fact, she's the she's the undergraduate TA, head TA, Ashley. She might be some of your lab leader. She's lab leader for one of the labs. And she also runs a lot of the other TAs. She actually got this question in a Google interview saying, hey, can you turn this trie into a compressed trie? And she had actually never seen it. She hadn't talked about compressed tries in her class. But she nailed it. And now she works at Google. Well, she's going to work at Google. So hey, that's important. So anyway, this is one of those structures that you should probably have in your back pocket to pull out during an interview or something. I do know another friend of mine from graduate school who works at Google now and said during his interview, somebody was talking about a data structure and said, how might you make this better? And he goes, I don't know, I might use a trie. And they go, good answer, you're hired. I mean, it was a little more advanced than that. But basically, they were like, whoa, that's cool. So yeah, sorry. Yeah, this one, you would have to think a little hard about how you might do that, right? You'd have to have now you say, OK, which letter, like maybe you have another little structure that says which ones are the ending of words. And it would be more advanced, right? But I think you'd have to maybe search less distance. But it would be a little more advanced. Yeah, just logic in that case. OK. So let's look at a couple things here. Just a little code. Don't make your eyes bleed too much. So this is a search. We're searching for the string. Now we already went through how to do this kind of in principle. Basically, it's not recursive. There's a little while loop here, but you are going to basically step through the length of the word, character by character, and then you're going to find if the current node's child exists. And if the current node's child exists, that means you have to keep searching. Like if you're searching for fish and the root node has an f as one of its children, you go to that f, temp, and then you set current equal to temp, and then you check for I. And then you say, does the new current have an I? If it does, you go to the next one, et cetera, et cetera. And if you don't find the letter, you return false and say the word does not exist. Right? If you go to the end of the word, what do you have to check? If you go through all these and you don't return false, what do you have to check? If it's a word, by the word marker, you return true. And then otherwise, you return false. OK? And if you don't even, like if you end up getting through, some of this is probably redundant. Like some of it might be a little bit redundant. But the idea is walk through each character, check its children, then check the children of that child, et cetera, until you find the word. So far, so good? Yeah?
So if you had cowbell in there,
Mm-hmm.
and you looked for cow, it would return false because it's not a word marker there.
There would be. Oh, if you had cowbell but not cow, right, what would it do? It would look for C-O-W, and it would find all those. Then it would get to here, and it would say, is it a word marker? And it would say no.
Okay.
Right? And then you return false. Yeah, good question. OK? All right, so a couple more things on this. Here's how you actually do the find child. This actually looks a little bit like magic. It's not, but it looks a little bit like magic. OK? You're returning a node pointer, and you're trying to find a particular character C. You return, if you have an array of 26 letters, 0 might stand for which letter? A. 1 might stand for, 25 might stand for Z. 0 through 25, A through Z, right? This is exactly what you were talking about here. in the array, you can actually take a character, which, by the way, is just a number. And that number, you can subtract out a number from a number. Guess what? If you subtract the character A from the letter, let's say the letter was S, which happens to have this thing called an ASCII value, because your computer gives values to these characters. In fact, I have an ASCII table on my computer here, right? And it looks like this. And if I hover over some of these, so like A over here, right, is 97. OK? What do you think B is? 98. They were smart about that, right? C is 99, et cetera, all the way up to Z, which is 122. And then all the other letters fit in there. And they made it specific. They thought a lot about this when they did it, right? But what that means is if you had A, which was 97, and you're subtracting the character A, which is 97, what's 97 minus 97? 0. That would give you the first one, which we said corresponded to A. If you do S, which is 115, minus A, which is 97, you end up getting 18, which happens to be the representation in your array for S. OK, so it's a one-liner as far as returning the place in the array. It would be more advanced if you had a linked list. But if you're doing this as an array, it's kind of neat that you can get the value out of the array by actually subtracting away a number, because these are just numbers. C happens to be whatever number character you're looking for, A through Z. And anybody from Canada? A through Z. And if you were looking for any particular letter, it will just subtract out A, and it will give you the position in the array that is corresponds to that, right? So it's kind of neat that way. All right, questions on that? Practice it, or look at the code a little bit. It's kind of neat. OK? All right. Do or do not, there is no try. Famous Yoda expression. And if you didn't recognize that was Yoda, shame on you. So yeah, he said, I don't think he meant that kind of try, but that's what I'm saying he did. OK, any questions on AVL trees or tries at this point? OK, all right, I'll see you guys Monday.